Hi everyone, thank you for joining my talk today. Today I'm going to talk about improving robustness on seasonality-heavy multivariate time series for anomaly detection tasks. Multivariate time series anomaly detection is an important problem with various applications from satellite systems to cybersecurity and fraud detection. Such models need to have some properties. First of all, they need to capture temporal dependency and intercorrelation between time series. The detections need to be timely, accurate, and precise, and also it is desirable for them to pinpoint the root causes. As an example, on the right-hand side, you see that the bottom and the top time series are contributing the most to the anomalies in the shaded area. So we expect that our model would be able to pinpoint those two time series as the root causes. There are some challenges associated with designing such models. First of all, they need to be trained in an unsupervised manner. The input data might have contamination and multi-period seasonality patterns, so our model needs to be designed in a way to handle those complications in data. In this study, we utilize GAN-based architecture, mostly because they have shown great power for image anomaly detection in previous studies. However, their application for multivariate time series data is still underexplored. Also, GAN's architecture are trained in unsupervised manner, which makes them more appropriate for this type of task. As a result, in this presentation, we propose robust seasonal multivariate GAN that we will go into the details. In general, the architecture of GAN for anomaly detection is composed of a generator and a discriminator. The generator has an encoder-decoder structure that tries to reconstruct input X using the contextual or reconstruction loss. On the other hand, the generator is trying to distinguish between the input X and the reconstructed input X prime by using an adversarial loss. The whole framework is trained in an adversarial manner by combating by the generator and discriminator combating against each other. After the framework is trained, we define an anomaly score by fixing the parameters of encoder-decoder and using the reconstruction loss. The intuition behind this definition is that we expect for the anomalous input in the prediction phase to generate large reconstruction loss, and this way we will detect those as anomalies. Our proposed RSM-GAN architecture follows the same structure with an additional encoder that is trained simultaneously with other parts of the network and by defining a latent loss. This latent loss is trying to optimize the reconstruction of the latent space. And we believe that this alteration to the framework would improve robustness of the system to contamination in training data. This is because even anomalous input will fall close to other similar samples in the latent space, and our model would be more robust. Now we will go through some detailed structure of this framework. Starting from the input, we first convert the raw multivariate time series to image-like a structure to be compatible with the convolutional layers in encoder and decoder. We do so by defining a multivariate multi-channel correlation matrix or MCM. And first we define windows of 3 different sizes. Within each of these windows, we calculate the pairwise correlation of the time series that will generate an n by n correlation matrix, and we do so for the 3 windows. So at each time point t, we are going to have a channel of the 3 channels of n by n images. We do the same thing for the whole span of time series by defining a step size S. As an input to our framework, we include MCM at time point t in addition to each previous steps as a sample so that the model can capture temporal dependencies. With such an input, our generator needs to capture both spatial and temporal dependencies. Therefore, we add convolutional LSTM layers to this structure. Furthermore, we need to adjust the seasonality patterns within this structure. And we do so by adding attention mechanism to convolutional LSTM layers. We do so by appending the previous seasonal steps to our input and let the attention weight mechanism to decide which of these previous steps are contributing the most to the reconstruction of the input. Therefore, for each input at time step t, we append each previous immediate steps as well as an arbitrary number of steps from different seasonalities. There are daily and weekly seasonalities in this specific example. Finally, after the whole framework is trained, in the prediction phase, we fix the parameters of the network and we define anomaly score assignment by using the residual MCM. Residual MCMs are defined as the L1 loss between the input X and the reconstructed input X from the first channel, which is associated with the smallest window while we were generating MCMs. Then if we assume that our input has 4 time series, this residual MCM would have a 4x4 shape, and we define broken tiles as the cells of this matrix with error more than a threshold. Those broken tiles are highlighted in red in this example. Then we define anomaly scores as the number of broken tiles in each rows and columns with more than half of the cells being broken, and the root cause as the rows or columns with the highest number of broken tiles. So in this example, the anomaly score is calculated as 10, and the root causes are the time series 3 and 4 because those have the largest number of broken tiles. To evaluate RSM-GAN and our proposed anomaly score assignment framework, we conduct an experiment based on generated synthetic sinusoidal-based data and real-world encryption key data. As for the baselines, we consider isolation forest and one class SVM as classic baselines and MS-CRED as a deep learning baseline. This model has an autoencoder based structure with the same convolutional LSTM layers. The table in this slide shows the comparison between different models based on the synthetic data that we generated by regulating 2 settings: the contamination in training data and seasonality patterns in time series. First, we started by no contamination and no seasonalities, and the results suggest that RSM-GAN outperforms other baselines, especially for precision, F1 score, and false positive rate. Then in the second experiment, in the second block of this table, we add weekly and monthly seasonality to input. This improvement of our proposed framework is even larger in this setting, as we can see for the precision and false positive rate. Finally, we added a severe contamination to the training data, and the result suggests that our RSM-GAN model is more robust to those contamination as compared to other baselines. This figure shows anomaly score assignment by different algorithms over the span of time in the testing phase, and it shows the result for synthetic data that has both seasonality and contamination. The bottom figure shows the ground truth labels for anomalies, and as we can see, the first 2 classic baselines are producing a lot of false positives that are irrelevant to the anomaly windows. If we look at the MS-CRED results, we can see that this algorithm is detecting some of the seasonal patterns as anomalies, which will result in high false positive rate. Finally, our RSM-GAN framework is showing very good result by detecting all the existing anomalies, and no false positive is detected by this algorithm. Finally, this table shows the result for real-world data and synthetic data, and again the results suggest the robustness of our model to contamination and seasonality by showing the lowest false positive rate and the highest root cause recall. This is especially desirable for system operators because false alarms can be very costly, and the root cause recall is directing them to the origin where the problem is originated. To sum up, we demonstrated that RSM-GAN outperforms all the baselines for anomaly detection in both synthetic and real-world data, and we showed that this framework is robust to contamination through the additional encoder, and also it can adjust multi-period seasonality through the embedded attention mechanism. Our proposed anomaly score assignment improves sensitivity and identifies the root cause framework identifies time series contributing to anomalies more accurately. And with that, I conclude my talk, and I am happy to take any question that the audience might have. Thank you.